if you
I was gonna say.
okay.
I never throw anything away.
Okay, everyone, let's begin the polymer physics class for this semester. No exciting, no claps? Let's do it. That's such a cold start. I give you a 6. All right. So, let's get started. So again, I'm Shodan. I'm going to teach you guys about the first part of quantum physics. And my goal is to make it simple, easy to understand, so you guys want to study the next 2 class next semester. Okay? Make sure I achieve that goal. So, first I want to give you guys some basic understanding what is polymer physics study in the first lecture. You know, chemistry is very straightforward. You think about what chemist does is playing Legos, and you put different building blocks to build something up. And I'm sure you guys have played with it while you are kids. So there's so many combinations. You can put a red color first, green next, or mix match. There's so many combinations. This is like very simple analogy. But how about polymer physics? What does polymer physicists do? Anyone can help me? Give me some clues. What polymer physics study? Spaghetti, yeah, good one. You learned something from last lecture. Anything else?
Molecular movement, vibrations, stuff like that.
Right, chain movement. Molecular interaction, that's another one. Additives, that's a little more like cooking a dinner. You're putting everything together now. So think about the simplest system. What would you study polymer physics in the first class? What's the simplest polymer physics problem you want to study? One chain. If you can, the logic behind this is, hey, if you look at everything, you know, it could be clothes or anything. Right now we are living in a macroscopic world, which means everything is big, large, you can see in your eye. As you know, the eye resolution is about how much, 100 micron or 200 micron-ish. But a lot of functions happens at very small scale. So many years ago in the 1960s, there's a famous professor called Richard Feynman. He gave a lecture called "There's Tiny Things Under the Bottom." In other words, he's the guy or the father opened the field of nano engineering. So all the nanoscale things started to open up. So if you think about my clothes, if you really zoom in, you're looking at individual molecular structure. So you're gonna look at a macro scale from millimeter down to nano. I mean, it's a buzzword. Everyone knows these days how big, how small that is. And why does this matter to us? And I will explain to you. Think about anything big scale, all originated from the nanoscale. That's a building block. Very tiny stuff really determines the macroscopic scale. So in terms of polymer, let me first refresh you some of the ideas how big everything is. Can anyone help me? How big is a carbon-carbon bond? 1.54 angstrom. Okay, that's a size scale between 2 carbon-carbon bonds. Now, I want you to think about what's the relative size scale about a polymer chain. Let's use the example for polyethylene. PE. The structure is very simple, right? Let's give it an arbitrary molecular weight. $280K Dalton. That's about the similar size we would expect in many commodity polymer. This is a little bit on the big size. 28K is relatively large in terms of degree of polymerization. We're going to use this as an example. So you guys haven't learned the class for the molecular weight, right? We haven't do that. Let me go through briefly what it is. So that is molecular weight. So how big the molecular it is. And if you count how much monomer molecular weight is, you can get a concept called degree of polymerization, or DP. So DP is basically molecular weight divided by monomer molecular weight. So let's call it MO. So you can see this is a total molecular weight, which is about 280K. Monomer, how big the molecular weight is? 28. Straightforward. So you got a DP, or how much you polymerize it. So DP1 means it's just a repeated once. So DP is basically this tiny m. So you can get it's about 10K. That's how much repeating you have this one. Now, while we do polymer physics, we start with the most simplest ever term. Forget about the complication, additives, etc. Let's start with the most ideal case. We are the only polymer chain in the whole universe. You are the only polymer chain in the whole universe. So, and how much you repeat yourself are? 10K. And let's say, think about this as a sort of uncooked pasta for this polyethylene. So it's straight chain. How big that is physically in the space? How big it would be? Can anyone help me in terms of length?
10,000 times 1.54 angstroms, 15,408 angstroms.
Very close, yes. But if you look at closely, we are looking at N, while each repeating unit has 2 carbons. So you just multiply it by 2 would be what is, we call it the length, okay? Let's put it for a length scale. That will be 1.54 multiplied by 2 multiplied by 10K. So that will give you about 35. Or 3 micrometer. So that's how long, if you are become uncooked pasta. Okay, so 3 micron, about the size scale. It's still in the micro world, but it gives you some idea. Now let's play another mind game. What if I say we now trying to play a game called knitting? We're trying to put as compact as possible for this polymer. Trying to squeeze it from a long pasta. Now crash it into real world is not a random core. Because the thing about random core or the cooked pasta, there's still voids in between them. You can still sort of messy ways, don't do that at home. But if you pick up the whole cooked pasta, if you squeeze it, you can still make them smaller, right? Smaller than the bowl you have. So my concept is how small this would be if we squeeze into the most smaller scale. That is relevant not only in a mind game, but in physical world. There's cases that your polymer chain will be compact. Let me give you an example. Think about you dissolve a very nice chain in a very good solvent. So chains are swimming along, they're happy, they were sitting in a good solvent, and they're cuddling together with all the solvent molecules. But somehow scientists decide, I want to purify it. Why don't we dump it into a non-solvent? Let it precipitate out. In that scenario, your chain is not totally dissolved anymore. It starts to collapse and form some structure to the globular structure. So that is something that really compact. So physically, how big that will be? Anyone can help me? How would you solve that problem?
You need to
Please.
know the,
Yeah, you go ahead, Nathan.
I was gonna say, you need to know the radius of generation for your,
Okay, that's one way. How about, please, any suggestion?
How close that the bonds can be before they break
That's another good way to think about the problem.
of atoms.
Yes, because there's psychologically there's only one way you can bend the bond. The radius gyration is another parameter we will talk later in the lecture. We will cover a little bit, but that's not the most complex. Radius gyration is still sort of in the good solution, so there's still some faults. But think about using a density as a way to approach the problem. So you know how heavy your material will be? If you divide by the density in solid states, you can actually calculate how much volume it will be, right? Think about it's a compact dense ball, something like a baseball. Think about that way. If you know how heavy the baseball is, if you know the density of the baseball, you can calculate the volume, then you can get the diameter. We won't need to go too much into that, but I'll give you an idea how you can get that. So let's say put it here. So still we got 180K PE. Now it's in collapsed shape. So you would expect molecular weight divided by density of the PE, and there is some constant, but Avogadro constant, and you can roughly get it to be, and that equals pi radius 3 times, so you can get radius about 50 angstrom or 5 nanometer. So if you compare, this is a size scale difference. This is about 3 microns, but now you start to squeeze the pasta into a solid ball. All of a sudden, your volume is dramatically reduced to a size scale about 5 nanometer. So that's about 600 times difference. It's quite a huge difference. To put that in real perspective, if you think about holding this guy in your hand, in physical world, as a baseball, you can hold it in your hand. How big that will be. So this is roughly as big as the size of a football field. That to give you a direct comparison in real life. So you want a football field, that's how long. The length, if you pull the polyethylene chain really straight, and if you let it all curl up, you can pack it into something in your hand as a baseball. So that's something problem is on the physicists trying to understand how the chain packs starting from single chain level, then to bigger scale in solids and in other material. Okay? So we're gonna start teaching about the most ideal model. What would you think that's most ideal model in terms of a single chain? I mean, pasta and etc. is very easy to understand, right? But in physics world, there's a special term for most ideal model. Anyone can help me again? I saw you was nodding before. No? Think about what would be influencing the size scale? But in reality, you would neither sit it into a straight chain, or this is a very compact dense. In real world, what would you expect is a chain? Something looks like this. Imagine this would be a power cable, Ethernet cable. Everyone uses it at home after using. If you're a very clean guy, you would fold it up multiple times and tie it into storage. Or you could be as messy as me. Sometimes I just throw it into the column and forget about it until several days later and say, oh, it looks so messy, let me put it. So the state of you throw it in the corner, it's capable randomly move it back and forth. It sort of resembles the physical state of how the polymer chain packs. So this size scale is not, let's still use 280K as an example. It's not like a globular, which would be super dense, there's almost nothing in there. Neither will be a straight chain, like on the other case. It's somewhere in between. And the first part of this lecture is help you to understand what is this and how big that will be. Okay? And I hope after 3-4 lectures we will understand several chain models and how we can calculate, given a polymer structure, how big it will be in several chain models. So I'll first give you a recap what the models are. Then for each lecture, we will cover one part of the model. And I want you to think about what would be the simplest model. Most simple. As simple as a bee. Random coil. That's the end product. This is essentially is a random coil. But let's say, let's assume, because if you know the polymer, if you zoom in really in this section, what you will see is basically the carbon-carbon bond, right? So if you look at it really closely on tiny scale, this will be carbon-carbon bond. In most ideal case, I would call it, there's no limitation in terms of any rotation in these angles. So it's totally free joined to the chain. In that scenario, that's most simple. And so that if you think about throwing a cable on floor, it can adopt any angle in terms of rotating the bond, right? So there is a physical term. Like it turned out to be the physicists really like to use some of the jargon to make it really sounds complicated, but it's relatively simple. So let's call it a model 1. It is called, turned out to be called free joint to the chain. So this is the fundamental basics for the whole class of the lecture 1 is how can we understand what is free joint to chain and how does it matter for us in the polymer physics problem. Okay, free joint to chain. In other words, everything is random and free to rotate and move around. You don't need to worry about any angles in between. But in real life, if you think about a bond, you cannot have a bond sitting at the same space at once. Think about, let's say, use this as an example. You have a carbon-carbon bond and another carbon bond. So free joint to chain basically means this bond and this bond can form any angle. Not only rotate around this diagram, it's free jointed. It can also rotate out. So think about it's a sphere that can rotate in all the angles. But in reality, of course, it's not going to happen. The reason is, if you sit on this chair, I cannot sit on the top of you again. That's not going to happen in real life for sure. But only happens in this free jointed chain model that your second carbon bond actually can rotate back and sit on top of each other, and that's without any problem. But even you are elementary school kids, you will tell Dr. Gu, that's not real. It's not gonna happen in real life. How far is this model from the real world model? Quite far away, to be honest. You're not gonna finish the polymer physics class by just studying this one. You have to consider many factors that influence it. However, this is the simplest system that you can study the polymer physics problem without worrying a lot of mathematics, etc., and would simplify your problem. So, coming to a little bit more complicated or realistic model. What would you think? What's the restriction we need to give it if you want to approach the reality a little bit closer? Steric hindrance. That's a very good call. Any bond sort of have a little bit angle. So, if we want to approach reality a little bit closer, we have to do something to change it. The first change, we're going to go through this first lecture, is coming from something free join to chain, something a little bit closer to reality. So we're going to come to the model 2, and you write on here. Rerotation model. So what does this means is now think about my angles, my joints as one example in terms of polymer chain. So in the polymer chain, in the first model, I can do, I'm not as flexible as this guy, but at least I can do this angle from 180 to about 0 degree. And I can also rotate this direction, right? So what does this guy, free rotation model, do slightly different with free jointed chain is now I'm starting to get closer to reality. What I would do is basically, like one of the students said, I'm going to consider angle. So let's say this would be the angle I'm going to fix. Let's call it theta angle. There's several cases you would know. There's a bond angle in quantum chemistry. If you have sp3 hybridization on the chain, you're going to fall a tetragonal, right? Then there is a certain angle for this bond to be. Okay. So if we consider the angle is fixed, we are getting a little bit closer. But we don't fix this rotation. So let's assume we're now holding an umbrella. Think about the umbrella is each umbrella versus the center axis, it has a certain angle, right? If you fully open, that's about maybe 70 degree in terms of angle. So if you hold it, the angle between the umbrella let's say it's fixed to that 70. So think about this, the angle is fixed. But however, you can rotate the chain. If you only see one segment as carbon, 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 you won't see much. But if you extend now, if you rotate, and this could also rotate, if you combine all the rotations, now you have a lot of combination. That is slightly closer to real world, since in real world the chain can rotate and chain has a certain fixed angle. We are sort of 60-70% to the reality. This is far from reality. But how can we use the model and further improve it? That comes down to the third model we're going to cover a little bit in the last part of the class. It's getting more complicated, I know. So hang on with me. What would you think the last model? And what's the restriction when you give it?
So your data's going to be changing based on properties of its groups.
Right, certainly. So theta will depend on different chemical groups. So for this class, let's stick with the polyethylene as a good example, because that's the most simple chemistry, right? It's always carbon-carbon bond. And we can think about this rotation, but let me give you a little bit of hint. So if you think about two carbon-carbon bond, and there's 3 more here, and this right now is free rotating. Please, there's
Minerals
questions.
forces will limit the rotation.
Yes, so different rotation angle will be limited by how bulky your group is. So the last model we're going to talk about throughout this course, and I'll just give you an overview, will be related to rotation angle. So how does it matter? Let me give you an example. Let me show you something called rotation isomer. So in this way, we are now looking at all the carbon bonds from a side angle. Now think about it, I am Superman. I can stick my head into the blackboard. Now I can look this way. What you will see is the carbon. There's 2 hydrogen, and there's another carbon, and the chain continues to grow, right? That's basically polyethylene. And there's going to be another bond coming out of the blackboard, then hit another carbon. So let me draw another carbon shifted here, and it will have another 3 stuff comes out. And we'll have 1 carbon, 2 hydrogen, and this one continue to. Now, think about this as a puzzle game. I'm not sure how many of you play the video games, but there's a lot of video games trying to give you a puzzle. The puzzle is basically a rotating stone. Depending on how you rotate, you can unlock it. And you would see the locker in the gym has used a similar concept. So now think about this as this. We're going to fix this carbon, put a nail into that. Now it looks like a fidget, we can spin it. Same as here, we can spin this guy as well. If these are, everything is a hydrogen, so let me show you. If the top one is hydrogen, this is also hydrogen, then the rotation is relatively, there are only going to be 2 states. One is, let me try this. One is everything is sitting on top of each other. There will be more steric hindrance. The other case will be one looks like this, the other looks like this. They will be happy because you didn't have much steric hindrance from the other one in the bottom. Same happens here. Well, we consider the rotation of the chain. There's a certain energy minima we need to adopt. This is really abstract. Now I give you something you can think about as a free energy. I'll think about this as a physical well. Something looks like this. What does this does is basically means this is rotation angle. Let's call this phi. How big it rotates depends on energy. So this is where 2 of the bulky groups sitting on top of each other, which makes the system unhappy, right? And this would be local minima, where you adopt different shape between 2. Okay, if we consider that, we're gonna adopt this third model, which I will talk in much more detail in the following lecture. Is called the rotation model. Basically, as the words explain for itself, while you rotate, there's some hindrance, prevent itself from adopting a certain angle. All right. So it looks like we don't need to study for the next month. Everything we need to teach is done. Shall we end the class? I guess no. So let's talk a little bit detail about all these individual ones. Starting with some mathematics now. Three-chain model. Three-joint chain. I start to use abbreviation. Now I'm gonna give you some background knowledge in terms of ideas about scales and vectors and etc. Because in the real chain, as I draw, let's use a little bit simpler one. If you break this down, I like to take this part. This looks better. It's basically one carbon-carbon bond, then another carbon-carbon bond, then the third one, and fourth one. If you zoom in really big in there, you will get something look like this. And next it would be a little bit fun. How many of you knows what is vector and what's magnitude? I think I asked you in the last class a bit. So good, half of the class, at least. Wonderful. So let's do this. I'll give you some knowledge. Think about I am the turbo driver. Now the group decided they want to go for a fancy dinner in New Orleans. There's many good restaurants there. If you guys want to hear about that, talk to me after class. Let's say we want to go to Commander's Palace. Wow, it's a good restaurant there, really good food. Their dessert is fantastic. How shall we go there? If you look at Google Map, you know the distance? This is about, let's say about 120 miles from, let's see if my math is good. So this is roughly where we are. Here is New Orleans. I don't know Louisiana that well. I live in Louisiana. Let's say it's here. So Google Map tells you should drive like this way. What you will read from that is the distance, right? It will tell you the distance of, what did I say? 120 miles? Right? But it only shows you this way. So let's say I don't have a GPS. I know I want to drive 120 miles. I could be anywhere on this circle, right? So now I'm going to introduce a concept. Let's say this is called magnitude, is a distance. What I tell you 120 miles plus southwest, maybe put a little bit more confident, 25 degrees, because there's no road that's straight, but you got the idea that if you keep that distance, that angle, roughly can reach New Orleans. But nowadays every kid has a smartphone, so no one would do this stupid thing. But while my father generation, they only have maps, so what they do is, I have to keep driving southeast for a certain distance. But you got the idea. If you have two components in your length and direction, now these two are different. Let's call it case 1. This is case 2. 1 is just the distance. 2 is now distance plus the direction. That's a vector. So the key of this guy is two components. A magnitude and direction. simple to understand, right? Let's play a little bit more to strengthen your ideas about the difference between two. What if now I want to go to Houston to see the Kennedy Space Station? Oh, it's so cool. My son started to love all these spacecraft, etc. So that's definitely on my to-do list. So think about this case now. We're gonna have another drive to the west. How far is it away? Can someone remind me? 6 hours-ish?
6.5 hours, yeah.
So that's about maybe 400 miles, 120. It's Texas, so let's give it a start. Okay, here we go. So let's call it a vector, A and B. So now if I want to know where to drive, I need two components. I need a second direction, right? So let's break down into A and B. So if I use some concept called A plus B as a vector, now it's slightly different with magnitude of A. There's a mathematics called magnitude. So this is a symbol for the vector, by the way. It has a tiny little arrow on the top of that. So that's basically a vector A, this is vector B. And if you put this is called 2 dash, it's an operation called absolute. What it does is do a simple thing is remove direction. So if I take A absolute, what will give me is just 120 miles. Now it's become a unit. Okay? Is this clear to everyone? So if I do this, can someone help me? If I use a magnitude, A plus B, this would be, A is 120, right? B is 400, that will be 520 miles. Now it's just a simple thing. There's no direction to it. Okay? So now, how about this one? Those guys who study vector, please help me. What it will equal to? What is A plus B in terms of vector? Anyone?
Well, it gives you like a linear line from the start of A to then B.
Right. You got a new vector. If you add a vector to another vector, you will get a third vector. And how does it work? It's very straightforward. So you take the starting point, and you take the final ending point, you draw a line. That's a new vector, see? But the distance is now not 520. It's becoming a new number that is somewhere in between. Right? And how, in real life, how much it is, you need to know the angle between these two to calculate that. Now it comes down to elementary or middle school mathematics to calculate a triangle. Why it matters? Because what we're going to teach about in this class uses vector concept a lot. Think about the simplest term. Now, I want to come back to this. Forget about all the Greek food and Houston. Let's come back to quantum physics. Think about what matters in quantum physics is you throw a polymer chain, what it matters is how big the cloud in physical size, or you want to know roughly how big they occupy in space. Okay, and or for example, what's the distance from starting point to the end point? From the beginning point to the end point. From the beginning point to the end point.
It's just a sum of all the vectors from
Right.
between every curve.
Exactly. So now, think about these are individual vectors. This is vector 1, this is vector 2, this is vector 3, 4. You just add everything up, you will get a vector look like this, right? That will tell you what's the end-to-end distance. And that is very important for the polymer physics to see how big your material is. Alright, it sounds very straightforward. But there are some other mathematics we need to cover, a little bit more complicated than just adding, A plus B. And there's a very weird operation in vector. I had so much trouble when I first time heard about it. It's not multiply, it's called dot ply. Oh, it's so confusing to me, but let's try to understand what is it. So, plus, you learn, minus is the same. If you have A minus B, minus is just to flip the direction. So, let's draw this again. We have A. This was what the B original is. Minus B, which is turn the direction. Yeah, way to go this way. So what the new C will look like this. Okay? Plus minus is easy. Multiply is also easy. What about 2 multiplied by A vector? It's just twice the length. Okay? Nothing fancy, because the direction is kept the same. You just change the magnitude. Well, how about this messy one? Alright. It's called dot multiply. A dot B. Oh, this is so confusing. It's not a cross, it's not divide, but just a simple dot. Anyone? In the back?
A times B times the cosine of the angle between them.
Yes. Perfect answer. So, let's say this is A, this is a B. Now we have an angle. If you think about this project, there's an angle theta. If you use a dot, multiply. A vector multiplied by a vector. How does that work? I want to go to Houston, this is a vector. I'm going to go to New Orleans, this vector. If they multiply each other, it's actually no longer a vector, just a value. How confusing that it is. In reality, it is. So what do you multiply these two? You lose the property of vector, so you became a magnitude of A. How long they are? Magnitude of B. And dot cosine theta. So I'm sure you guys will understand what cosine theta is, which is basically this. So there's a physical meaning into that. So dot product is basically trying to understand how much component of the B vector is flowing to the direction of A. Think about what is second half does. B multiplied by cosine theta. It's basically this line, right? The cosine theta is this line. This is sine theta. So we're basically trying to get how much B component still falls into A. And this is a little bit confusing, but please memorize this. How does the dot multiply work? Okay? And there is another thing we want to quickly cover, is something called a sum function, or how you write adding everything together. There's a mathematical term for that. So let's write a little bit here. Oh, I'm sorry. So this is a sum function. It basically says add everything together. So if you write Ln, it means L1 plus L2 plus Ln. Okay? So let's take a short break, take a 5 minutes break, then we will continue to talk about free jointed chain. And we can chat another 20 minutes or so before we wrap up the class. All right?